So at this point, we have a way of finding these tangent lines and calculating the slope of these tangent lines. And like I was showing yesterday, the idea is that we should be able to say a small change in the x coordinate is equal to, say, a small change in the y coordinate up to some conversion rate, right? So that would be my slope in this case. So this slope idea, this conversion rate idea, is called a derivative. Now, this is going to come up whenever we try to calculate rates of change for any function. The way that we typically teach calculus is, I'll say, agnostic to use case, because at the end of the day, we've got some function, some dependent variable, we have some independent variable, and we're trying to measure relative rates of change. And the actual calculation is going to be the same whether our numbers are representing position or volume or energy. So let's assume that all of these limits exist. We have seen limits which don't exist. If they do, then I want a new function which will record the values that I get for the slopes of my tangent lines. We've already been seeing that I could have different tangent lines with different slopes depending on the coordinate that I pick. Now this gets a special notation. I'm starting out with some function f. I don't know what its formula is. The derivative of f, I will give the name f prime. So if I have f of a as my original function, then f prime of a is its derivative. Or if I had g as my original function, it would be g prime as the derivative. If I had h, well, I'm already using h as my variable here. Let's say I had a function that I'm calling d of x, then my derivative would be d prime of x. And the prime here, when I write it down, is just a little tick mark, just an apostrophe after the letter f, or the letter g if your function is called g. We keep them the same letter to help associate the two in our writing. So for any coordinate a, I need to tell you how to find f prime of a. I need to tell you what number the function is supposed to output. So as long as this limit of the difference quotient exists, the function f prime of a will be equal to the limit as h tends to 0 of f of a plus h minus f of a, all divided by h. So notice that this limit does not include direction. So this limit is only going to exist if it's our two-sided limit. And we have all the usual conditions about limits existing or not existing as well. I could have also written this formula differently. I'm still going to keep my f prime of a the same, but I could have also used the formula where I take the limit as x approaches a now, and my difference quotient formula says I need to calculate f of x minus f of a, all divided by quantity x minus a. These two different formulas are just different ways of writing the very same thing. So here, x is equal to a plus h. And if x is approaching a, then h has got to be going to 0. So let's use this formula to calculate a derivative of a function. Here I have a nice quadratic function that, I know it's not a line, but I can still associate this idea of slope to every single point on the picture of my graph. So let's do the algebra work. How do I find the slope at coordinate x equals a? That's what the derivative measures. So I would write f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a all divided by h. That's going to be the same exact formula every single time. That's the limit of the difference quotient. Let's actually put in the formula for the function. So the formula this time is x squared minus 8 plus 9. So here I have the limit, and I've got quantity a plus h squared minus 8 times quantity a plus h plus 9. And all of that is minus the quantity a squared minus 8a plus 9. That's my numerator. All of that's divided by h. Just like we saw, the denominator of this limit is going to 0. But so is the numerator. So I am expecting that there should be some cancellation here, and that after that cancellation, I can factor an h out of the numerator. So let's actually do that. I can FOIL everything out. Again, this is work that requires care and attention, but it's not something that is conceptually difficult at this point. It just takes a little bit of time. I notice that I have a positive 9 coming out of my first term on the numerator. I have a negative 9 coming out of the second term of the numerator. And similarly for a's and stuff like that. After cancellation, I'm looking at the limit as h goes to 0 of twice a times h plus h squared minus 8h all divided by h. And I can cancel just like I said I can. I can factor out an h and say that this limit is equal to the limit as h goes to 0 of twice a plus h minus 8. So I get 2a minus 8. Easy peasy.